So this work is my joint work with my supervisor, Dr. Gautam Paul, and our collaborator, Dr. Anand Banerjee. Anand is a postdoc at Center for Quantum Technologies at National University of Singapore. So the title of my talk is Maximum Violation of Monogamy of Entanglement for Indistinguishable Particles. So this work is based on our paper of that is published in 2021, that is maximum violation of monogamy of entanglement for distinguishable particles that are by the measures that are monogamous for the distinguishable one. Okay, so let's start. So this is a brief overview of my talk. I will introduce distinguishable and indistinguishable particles, monogamy of entanglement, then no cloning theorem, and then we will go to the main contribution of our talk, that is the degree of freedom trace out rule and the maximum violation of monogamy of entanglement for indistinguishable. So let us start with a puzzle. Suppose in an office, identity card is issued to employees to distinguish them and track them for some specific task. However, without the identity cards, they cannot be tracked individually. You can see in the following figure in the left hand side. So they are two identical employees, but they can be identified using their employee ID. Their employee ID is different. But here you can see two employees, they are fully identical. They cannot be identified individually as they don't have uh, any employee ID, right? Now, suppose the company gives some task to both of them. Now, there are some question arise that uh, both of the person having employee card and without having employee card, can the task be still be completed? Means both of the pair, can they still complete the task? And if both complete the task, what will be the efficiency of the task? Who will become more efficient for this task? Does there exist any specific task which can only be done with this distinguishable employees or this indistinguishable employees? Okay. So we address this question, but when employees are replaced by particles. So as we see that in this figure or in this context, you can see that okay, these questions cannot be answerable or something difficult, but we have an answer when we move to the quantum domain. Okay. Let us introduce distinguishable and indistinguishable particles. All the particles in the world are basically either identical or non-identical. So here you can say non-identical particles are always distinguishable. You can always distinguish the non-identical particle by their any of the properties like color, spin, and other. Two particles are said to be identical if all their intrinsic properties, suppose mass, electric charge, spin, color, are exactly the same. Now, identical particles can be distinguishable, can be indistinguishable. So, when two identical particles are indistinguishable, means bosons and fermions where each particle cannot be addressed individually. Okay, let us address this part using this figure. Suppose two identical particles, this is red one and this is also red one, and they have this special wave function. This for this particle, this is special wave function is confined to S1, and for this particle special wave function is in S2. Now you can see there is no overlap between these two wave function of their particles. Now, so you can label these two identical particles as A and B. Then you can distinguish these identical particles. right? So identical particles by this way becomes distinguishable. But if their special wave functions are overlapped in S3, then you don't know that which particle is A, which particle is B. Then the identical particles become indistinguishable, right? So this is the basic way to make identical particles as distinguishable and indistinguishable. So in our previous work, we have shown that there exist some properties that are unique to distinguishable particle and unique to indistinguishable particle. We show that unique fidelity quantum teleportation in 2020, our previous paper, is only a unique property of distinguishable particle, and hyperioid entangled state is a unique property of indistinguishable particle. And there exists some of the properties like entanglement swapping, coherence, metrology. They are unique. They are does not unique to any of them. This can be done using both of the particles. Okay. So let us introduce the monogamy. We all know that monogamy of marriage. What is monogamy of marriage in our social life? If we are married to some person, we cannot be married to some other one. So this is a monogamy rule in our society. So you may think, okay, why, in which context this example arises? But this rule has interestingly in quantum domain. How? Let us see. Suppose two particles, A and B. If two particles are maximally entangled, then none of them can share entanglement with any rest of the particle or any rest of the system. So the monogamy of entanglement in an equation can be expressed like this, that the entanglement between A and B and the entanglement between A and C, this amount of entanglement should be less than the entanglement between A given B and C. This is the equation of monogamy of entanglement. Now, you can say, okay, is there any application of this monogamy of entanglement? Yes, monogamy entanglement has application in quantum P distribution, classification of quantum state, condensed matter physics, even in black hole physics. So this is very important. Now, you can think, okay, this monogamy of entanglement, yes, does it always hold? Before answering this question, we have to know that on which properties this monogamy of entanglement depends. Monogamy of entanglement depends for two properties. One is the dimension of each particle, that whether they are qubit, qubit, or qubit, and the entanglement measure you are using, like concurrence, negativity, and other entanglement measures. So they always depend on these two properties. Okay, so for qubit system and concurrence entanglement measure, we always know that for distinguishable particle, monogamy of entanglement always holds. Okay, so dimension is 2, qubit system, and entanglement measure is concurrence. So for this, monogamy of entanglement always holds. But if we go to some other dimension, some higher dimension, and go to some other entanglement measure, monogamy entanglement may not hold, right? So for example, this state psi is a Q-treat state. So 1, 2, 3 is the Q-treat state. And you can see that for this state, monogamy of entanglement, like this equation, does not hold. So C square A plus C square AC equal to 2. This is greater than. So this does not hold. This is a paper of 2007. You can have a look at this paper for this details mathematical discussion. So so that's why when we are going to the higher dimension, monogamy may not hold, right? So we are confined our discussion for qubit system. So for qubit system, there are several entanglement features that are always hold, like Hong squared concurrence, log negativity, entanglement formation, trellis Q entropy, etc. Okay. So from now, we'll restrict our discussion only qubit system. Now, okay, there are some violations. We know that monogamy entanglement can be violated, but how much violation can be? Is there any limit towards the violation? Yes. So there are two type of monogamy violation. One is maximum monogamy violation, and another one is non-maximum monogamy violation. Okay. So suppose E is an entanglement measure, and for entanglement measure, there is always a maximum. So we denote this by max, the maximum value of entanglement measure. So if the inequality of one, say this one, if we have E of AB less than Emax, E of AC less than Emax, but they are jointly greater than Emax, like this one. So this one is an example of non-maximum violation. And the maximum violation is both of this one and this one achieve Emax. So this one, the maximum value is Emax, for this one, maximum value is Emax. So the left hand side maximum value will be 2 into Emax. So this we term as the maximum violation. Okay. Now I am explaining why this non-maximum and maximum value violation has so much impact. Okay, first of all, we all know that cloning has a different meaning for biologists and for for our quantum information theorists. So biologists successfully cloned a sheep in 1996. So this says biologist says, okay, we cloned a sheep, but quantum physics says, well, yes, but actually no. Why? We have a no cloning theory. No cloning theorem forbids the formation of independent and identical copy of any arbitrary unknown state, which was proposed in 1982. So it follows that from the fact that quantum operation must be unitary like linear transformation. So this no cloning theorem has a very much application in quantum error correction, cryptography, black hole physics, etc. Now, what is the relation between monogamy of entanglement and no cloning theorem? Yes, for distinguishable particle. So we are again in the domain of distinguishable particle. So for distinguishable particle, maximum violation of monogamy of entanglement implies cloning. Okay, how it can be done? Let us have this example. Suppose A is maximally entangled with B and A is also maximally entanglement with C. And phi x is an unknown state. If we have a Bell state measurement with phi x and A, and this output y is communicated to B and C, and they perform some unitary operation on y, on their particle B and C, then we have this unknown state on B and C. Thus, we have two copies of phi x in phi B and phi C. So this violates the no cloning theory. So this says if we have the maximum violation, then we violate the no cloning theory. Okay. But now we move the another picture where you can say there is some apparent violation. Suppose A is a particle having degrees of freedom A1 and A2. B is a particle degrees of freedom B1 and B2, and C has C1 and C2. Suppose A1 and B1 is maximally entangled and A2 and C2 is maximally entangled. Okay, if you uh, see from the particle point of view, like A, B, and C, so you can see that A is maximally entanglement with B, A is maximally entanglement with C. But you can say, okay, so this violates the monogamy of entanglement. Actually, no. If we again go to much closer look, like, so then you can see that A1 is maximally entanglement with B1 and A2 is maximally entanglement C2. And since E1 is not maximally entanglement with C2, this does not violate the monogamy of entanglement, right? So this state is proposed in 2015. Okay, so we can see that okay, the particle paradigm is somehow incomplete. So we need to go the degree of freedom paradigm when we will have a beta loop. So this we can refresh the monogamy of entanglement using the degrees of freedom picture. How? Let us see. Suppose the ith degrees of freedom of A is maximally entanglement with jth degrees of freedom of B. Then a ith degrees of freedom A cannot be maximally entanglement with any kth degrees of freedom of C. So this is the DOF view statement of monogamy of entanglement. So if we write an inequality using that, like previous one, like uh, this one, we can write that ith degrees of freedom of A and jth degrees of freedom of B plus ith entanglement between ith degrees of freedom of A and kth degrees of freedom of C is always less than between the ith degrees of freedom of A and jointly the jth degrees of freedom of B and kth degrees of freedom of C. So the monogamy inequality using DF can be written like this. Okay. Now we'll move to the indistinguishable domain. Okay. So for indistinguishable domain, let us denote. So there are two standard approaches for representing indistinguishable particle, like the first quantization method and the second quantization method. But here we are representing a much easier way for indistinguishable particle like this. This formalism was introduced by Lo Franco in 2016 and also improved in 2018. So we have taken their formalism for representation and we have represented indistinguishable particle using the closer view, that is the DOF. Suppose two indistinguishable particles have two DOF associated and the special labels are alpha and beta. So ith and jth DOF are represented by AI and bj. Then the state is psi2, that is a coefficient, and alpha a1, a2, beta v1, beta. And this is just the density matrix. Okay. Now we have introduced a degrees of freedom trace out rule. Okay, this may look very much mathematical, but this follows from the simple rule. Suppose for the normal trace out rule, if there are three particles A and B entangled, you trace out B, then you get the reduced value of A. But for indistinguishable particles, since we don't know that which particle is A, which particle is B, the trace out rule becomes more challenging. And if you go to the DOF trace out rule, then the trace out rule becomes more challenging because you don't know that which DOF comes from A or DOF comes from B. So if you just follow this formula, you can trace out the any DOF from any of the particles, right? So I'm not explaining this mathematics. Yeah, you can get this mathematics from the paper. I'm just now explaining our main result. Okay. So our main theorem is for qubit system, indistinguishability is a necessary criterion for maximum violation of monogamy of entanglement. So what we show that for distinguishable particle, maximum violation of monogamy of entanglement leads to violation of no colony. But for indistinguishable particle, this does not happen. Okay. For indistinguishable particle, we have a maximum violation of monogamy of entanglement by the measures that are monogamous for distinguishable particle, like concurrent. Okay. So this can be shown using a counter example, right? We have a circuit which violates the monogamy of entanglement maximally, but does not violate the nuclear. So this is the circuit of Lee et al., which is proposed in 2018. So for this circuit, so suppose Alice and Bob has two identical particles. So this is a hybrid beam splitter with, and this is a hybrid beam splitter is a combination of normal beam splitter and some other part, right? So this particle goes to the hybrid beam splitter this from this side and this particle goes to this side. So this circuit is basically a particle exchange method, which is proposed in 1992. They improved this particle exchange method for multiple degrees of freedom, right? this particle goes to this hybrid beam splitter. They can be go to this way or this way. This particle can go to this way and this way. So if we measure, we can measure either spin measurement for Alice, either and also spin and path measurement for Bob. So we show that each particle has 2 degrees of freedom, spin and path. So we show that the spin degrees of freedom what Alice measured is maximum entangled with the spin degrees of freedom of Bob, and the spin degrees of freedom of Alice is also maximally entangled with spin degrees of freedom of path. So this says we have a maximum violation of the monogamy of entanglement, right? So if you write this equation, the state of the equation can be written like this, and we show using concurrence entanglement measure as the maximum value of concurrence entanglement measure because is 1. So we show that the spin is 1 and spin path is always 1. So you can actually analyze the calculation in our supplementary material. I'm not going into the details of the supplementary material, but this essentially says for indistinguishable particle, we have a maximum violation of the monogamy rule, right? So now the most interesting part of this talk that okay, we violate the monogamy entanglement maximum. Then comes, so what is the fundamental law? So for distinguishable particle, we see okay, maximum violation of monogamy, violation of no cloning theorem. So both become fundamental. But for indistinguishable scenario, we have a maximum violation of monogamy particle, but no cloning theorem still holds. So which one is more fundamental? Obviously, the no cloning theorem is more fundamental for indistinguishable, right? The next question, obviously, from application point of view, that what is the application of maximum violation of monogamy? We see that there are some application of monogamy of entanglement for distinguishable particles. Then what will be the application of this monogamy of entanglement for indistinguishable particles? This still an open area of research, so we are still trying to uh, find application where we can apply this result. Okay, and the third one that okay, we have talked about like entanglement, but there are other quantum correlations like steering, coherence, discord, and monogamy property also applies to this correlations also. Now the question is there any this maximum violation for indistinguishable particle for this quantum correlation? We have to still find out. So there are plenty much areas which can be explored using our result, right? So this opens a completely new area. So there are maybe lots of papers can be done using this domain, and if any of the participants would like to work in these domains, so collaboration and they have some ideas, so I'll be happy to answer their questions. And yeah, so this concludes my talk, and thank you for listening.
Thank you, Mr. Dash, for this intriguing and interesting topic. Now the floor is open for question. I have one question actually, it may be a bit naive. How this violation of monogamy of entanglement affects in quantum cryptography?
Okay, so in quantum cryptography, suppose for QKD based for entanglement quantum cryptography, suppose Alice and Bob having they do this cryptography with the Bell pair, like Bell state.
Yeah.
For Bell state, the Bell states are always maximally entangled, right?
Yeah.
So for cryptography, it is if there are some Alice always try to have entanglement with any of the particle of Eve. Eve is a attacker. So you always try to do entanglement with any of the particle of Alice and Bob. If they can entangle any of the particle of Alice and Bob, then they can share some of the information between Alice and Bob, right? But due to this monogamy of entanglement, that if both are maximally entangled, then Alice cannot take any information from Alice and Bob. Just you try to repeat the mathematical details what the quantum cryptography has, like QIQT-91 protocol. Try to do with any non-maximally entangled state. Just follow the same state and you will get the answer.
Okay. Thank you very much. Any other question? If there is no other question, then let's thank the speaker for this very, very exciting talk. And let's move on to our next speaker, Mr. Anand Devranjan, who did his MSc from IIT Madras and currently doing PhD at IISER Kolkata. So let's welcome Mr. Anand Devranjan.
Hello, sir. Good evening, or good evening, all of you.
Yeah, good evening.
Thank you for your kind introduction. Should I share the screen, sir?
Yeah, sure.
Okay. Yeah. Is it visible now, sir?
Yeah, it's visible.
Okay. Yeah. So as sir has already given my introduction, so I will directly move on to the topic. My topic of interest, as you can already see, is 3D, that is three-dimensional polarization. Why I chose this topic? So first, this is a as I am from a mostly experimental background. So I'm working with Professor Anand Banerjee here at IISER Kolkata. So there is a link between the classical part and classical optics and quantum optics. So although this talk is not focused on linking these two, but I will try to motivate you that there is, if we even go forward with the classical optics, there are some glimpse of the quantum phenomena that really comes into picture. And what I chose as a probe for my study is polarization. As you already know that polarization is one of the most basic property of a wave, and that's why I will focus on this topic. Now, how the talk outline will be, first I will give a historical perspective of why I chose this topic and what are the various advancements that has been done in the field. And then I will try to relate that what are the various forms of polarization that exist. This topic, the topic will be completely focused on the classical part, and I will try to give you insight about how we can move on from a more idealistic system that we all know, that this two-dimensional polarization, to a more realistic system that is three-dimensional polarization. So what is polarization? So if we go as back as nearly 700 AD, there was the first, not say evidence, but first document of polarization. That is not scientific document, but from web series, we can say that Vikings, if you all know, then Vikings were the first group of people who used this Iceland spar. There is a crystal called Iceland spar for their navigation. Now, after many years, there has been any advancement in this relative field. After nearly at 17th century, Bertolini was the first scientist who gave an experimental verification of this phenomena, that what is light and what are this polarization. So what he observed is, he observed two images in Iceland spar, and for that he published an experimental paper. As you can see in the right side, this paper in 1970. So this paper, he was the first who described this topic in detail, all the experimental details. Then the question became very prominent, that what is light? So previously it was thought that light is a scalar quantity. Now, means if I will give you a glimpse of what is this, what is his experiment work. So this is like this. If you, this is a calcite crystal. So what happens? These are the straight lines. If you draw, you can see that there are automatically two images that is getting formed when you rotate the calcite crystal. So at a particular axis, there are, means how a crystal can have a two image of the same thing. Means either there can be some component that is existing in that light, or there can be something else. So this remarkable experimental observation baffled scientists at that time, that means there is light has something else. It's not completely scalar. So after that, there was a huge one of the big pioneer of our field, Christian Huygens. He said that it says light is not scalar. There can be some other component also in this light. So after one of our pioneer father, means Newton also suggested that light had sides. A quote unquote, he said that light had sides. So what he meant, all these people meant is, the scalar picture of light is not enough to explain many of the new experimental evidences like of this Iceland spark. So after that, this started a debate that light has to have a vector nature. So means this vector nature, but there was no theoretical evidence, theoretical formalism to explain this thing. So the very first formalism that came was from Maxwell, and means before that there was means also Stokes, and which we will see now. The Maxwell equation were the first thing that totally proved the vector nature of light, and this vector nature of light is what we called as the polarization. Okay, this property of having this light having a vector nature is called the polarization. This is as simple as that. Now, if we go on to say that what is this, means we already know now this polarization. So how this propagates? So the Maxwell equation means if we solve the Maxwell equation, so means for in case of vacuum, what we get is a means wave propagation equation. Now this equation tells that there is a light can be considered as a wave moving with some speed c. Now there can be n number of solution to this equation, and one of the simplest solution of this wave equation is the plane wave approximation, that is plane wave solution. Now what in plane wave, what we assume is that if there is some means a plane wave propagating in along r direction, but we can write that plane wave in terms of this. So I am actually using only electric field, although there is also a magnetic field there. So I will mostly omit this magnetic field for just for convenience, nothing else. So here the means all the symbols have usual meaning that omega is the means frequency, and k is the propagation vector, and means E naught is the amplitude of the electric field. Now let's simplify this more further. So if we simplify this further and assume that the vector that the wave is moving only along the z direction, we can write this equation, this plane wave, in terms of these two relations. Now till this point we already know that means light is a vector quantity, and we can write it, one of the simplest solution is a plane wave. Now these two are the different two components of the wave. Now if what we do is, so if we just use this relation and we can tune it more further, what we can solve, what we will get is called polarization ellipse. Polarization ellipse is nothing, it's just means all solution of all the previous two equations that you saw. So we squared and added these two together, and we got this relation. Here delta is the phase difference between the two X and Y vectors. Now, as you can see that means why is it called polarization ellipse, since this has a mathematical form of an ellipse. So now there are so it's what is this? What is this relation? What is this equation? What does it mean? So it means that if you have a means plane wave propagating, if you take the consider locus of all the resultant polarization vector, that is Ex or Ey, so you will get this. You will get a ellipse. So this is it, nothing else. So in figure, if you look, this is like this. So if you can consider the green one to be the x electric field along the x direction, and red one to the electric field along y direction, and polarization ellipse is just like this. It looks like, as you can see, it looks like an ellipse. If you just see, if wave is coming towards you, it will look like an ellipse. Now, we finally found that there is a, in order to quantify this polarization, we have a polarization ellipse. But the problem associated here is there are a bunch of problems. I will explain one by one. First, the one thing what we can say about this is polarization is inherent property of a light. Okay. So any light wave will have a polarization, since it will have an electric field or magnetic field, which will make this light wave. So automatically it has a directionality to it, and that directionality will give its polarization. But what this polarization is, so what we have derived till now is only for parallel, only for what's the polarized light. So is there any polarization ellipse for unpolarized light? So we don't know. From the relation, we can't predict. But other problem is with this approach is this is a very very fast. Now, if you just assume that for a light wave of 500 nanometer, the frequency of its oscillation will be in gigas per second, and there is no detector at the moment which can take a snapshot like this. So we will be at the moment we are not able to see this polarization ellipse. So how you can even say that where, means how you can measure this polarization, how you can say where is this polarization? So this these questions ultimately leads to a requirement that polarization, although polarization ellipse proves that there is something called polarization that is inherent to the light field, but it do not gives a picture of a measurable quantity. We can't measure it, although we can predict it, but we can't measure it due to its very fast nature. So this has led to debate that what can be other formalism to address this concern. Now, the very first attempt that has been done was, and one more problem was that since this is based on idealization of light, plane waves are not, you will not see plane. It's an complete idealization. Most of the waves that if you see a laser beam, so it has a finite width. It do not have an infinite cross section. So that's why it can't be considered, you can't consider them to be a plane. So even at the idealistic situation, we can't measure it. So how you can be able to measure it for the realistic situation? That's why it requires that we need a better, more rigorous theory framework which can describe this polarization. And this framework was given by Stokes, and he gave something on the basis of measurables. So previously you can see that polarization ellipse was entirely based on locus of the resultant vectors. But here you can't measure the amplitude. What you can measure is the intensity. You can measure the square of the amplitude. You can't measure the amplitude. So Stokes came up with these 4 measurable quantities that you can measure by using polarizers or analyzers. So he gave 4 parameters. Those are called as the Stokes parameter. Now, using the same polarization ellipse, so if you remember that previous relation, we will use the same relation, nothing else. So what we will do is, since our wave means we will do the average. So any detector that we will use is means it will not be able to match even even 1,000 or 10,000 times of what the actual frequency of the light is. Hence why we can average average the amplitude and get a relation. And what we can get is finally 4 parameters. That is those 4 parameters, as you can see, are called the 4 Stokes parameter. And what are the significance of those parameters? I will explain just in a minute. Okay, the first parameter, as you can see, was it tells you the total intensity. It is just the amplitude square of both the both the polarization directions. Now the second, as you can see, is how much of one particular polarization state is more than the other. So, and the other two also. So what is the how much is the phase? Means it will tell you that how much is the right circular polarization is there or linear polarization is there. So all these together can describe any arbitrary set of polarization. So this is the achievement of the Stokes. Although Stokes, after publishing his paper, he didn't work on this topic at all. This was his one and only paper, but this was one of the remarkable achievements of Stokes, and it is still used till now. Okay, and so as you can see that if those Stokes parameter, if you just add these, they all together follow this relation. And we don't know why it should follow this relation, but this gives a very convincing picture that, see, S0 is what? S0 is the total intensity. Okay. Now S1, S2, and S3 are the combined intensity from the various polarization states. So the total intensity should be equal to the corresponding contribution from other parts. This seems very logical. Okay. Now, what seems more logical also, that what consider a more arbitrary situation, that you have a light that contains both polarized unpolarized part and polarized part. What will be the Stokes parameter for that? Okay, so this is for that case, what we will use, we will just use the Cauchy-Schwarz inequality, and what we can get is just this. So yeah, the total intensity should be is greater than equal to the contribution from the other parts. Here, the equal to is the case when there is complete polarization, and greater than is the case when there is a partial polarization. So this relation can describe any arbitrary polarization state of light. Now, you can say that, yeah, we have finally got that what is polarization, how you can quantify this polarization, but we still don't know how. We have always have a way of saying that how much is this polarization there. So this leads to quantity called degree of polarization, that it will tell you that how much polarization is there in that particular light field. So it is nothing. It is just we can say that it's the total intensity divided by the polarization part. Now the top part, as you can see, is contributed from the polarization, a polarized part, and the bottom is just the total intensity. So if the top part, if the numerator and denominator are equal, that means that it is totally polarized. That is P equals to 1. And if numerator and denominator, if numerator is 0, that means it's completely unpolarized. Okay, there is no polarization at all, and then it becomes 0. So degree of polarization quantifies this polarization, how much is the polarization present in the light. Now we already got that what is polarization, how is the degree of polarization. So are there there is also an alternate way to describe this polarization state of light, and that is given by the coherency matrix or polarization. This matrix is defined as just this phi ij. Ij are just the various places of the matrix, and as per definition, it is like this. Okay, Now you can see that the very first, the very first element of this matrix is the X contains the X part, and the very last element contains the intensity from the Y part. Okay, and this is time average of this. Now, can we relate the Stokes parameter to this polarization matrix? Okay, first, why is this? Why even this matrix is required? You already have a formalism to completely describe the polarization state. Why you need even this new formalism? First, as a physicist, it's easier to work with matrices, and if we using matrices, lot of linear algebra follows. We can use all the various algebra that is already been there for this matrix. So in order to use that algebra and to make our life simpler, we want to use this Stokes parameter in terms of this polarization matrix, nothing else. So as you already know, the first part is the X. So we can write all the Stokes vector in terms of this polarization matrix. That's done. Now this polarization matrix can be written in terms of this Stokes parameter. If you remember, this S0 is simply the intensity of all, and S1, S2, S2 are the components from the polarization parts. Now, this phi is what polarization matrix, and now these are the two different formalism that has been related. If we go further step further, can you figure out what is this? Can these metrics look familiar at all? I think you would already know that these are what is called as the Pauli metrics. Okay, so these are the famous Pauli metrics. So means, can you imagine? It gives. It's very surprising that how completely classical thing has this sigma you all already have seen in most of the quantum mechanics book, that means this sigma gives you in spin of two level systems and all. So yeah, how this sigma comes relating the polarization matrix to the Stokes vectors. Now sigma describes the polarization of any arbitrary field. So sigma is one of the what you say that generators, or one of the missing links that relate polarization that relates a polarization matrix to the Stokes vectors. Okay. Now this sigma is we can also write this degree of polarization in terms of this using previous relation. Now S1, S2, S3 can be written in terms of that polarization matrix, and we have a relation in terms of like this. That's all. So 2D, so we can represent completely 2D polarization state in terms of these two equations. Any 2D polarization state can be represented in terms of these two equations. So the bigger question is that why are there any three-dimensional cases? So this you have already seen that the vectors are in X and Y direction. So can there be any three-dimensional analog of this this polarization, or are there only two-dimensional cases of it? Okay, and the other question that is that can we transform this two-dimensional polarization matrix to three-dimensional case? Okay, using the sigma and other thing. Why sigma is coming here? Okay, how it has appeared in a classical topic. So this sigma is something that is a generator. Sigma is considered a generator of a group called SU2. SU is nothing, a special unitary. 2 is the dimension Lie group. What are those things? I will just tell you in a minute. Okay, so so do there exist a three-dimensional polarization state given by, so similarly to SU2 there exists SU3 Lie algebra, Lie group. So can we transform? Is there a way to transform this two-dimensional polarization to three-dimensional case? Is there a possibility? Since two-dimensional is a further idealization, can three-dimensional case we will be will be able to represent a more true picture? So the answer is theoretically it's possible, and we will first see a glimpse of what is group theory. So group theory is when you have an operation defined on a set, okay, and just consider that some operation is given by star defined on a set of objects, and it should follow four different rules. If those sets follow four different rules, then we can call that a group. So first is called the closure property, that all the elements of the group should belong to the group, okay, under that operation. So means one element with operated with some other element, the final product of that element should be a member of the group. And next is associative, that means you also know this, you would probably have known these things, that two consecutive one operation with other, and the consecutive operation of the product with some other element, finally both should relate to the same group. And the next is there should be an existence of identity, or if the arithmetic process is done with the member, if that identity member, it should turn out to be the member itself, and the existence of inverse. I will tell you, from an example. Just consider addition under, means you consider a set of elements given by capital R, that is the set of real numbers. So consider the operation to be addition. So if we add any two real numbers, it will always turn out to be a real number. So closure property is satisfied. So if we add any two real numbers, and if we add that addition to another real number, the final will be also a real number. So associative is also satisfied. Existence of any identity. If we add 0 with any real number, it will always turn out to be that real number itself. So identity is also there. And existence of inverse. So if we add real number with its negative part, -1 + 1 turn out to be 0. That is, so there is also an existence of inverse. So we can see that addition under real numbers forms a group. Okay. So similarly, we can say that there can be ways of there can be two ways of defining. So there can be a discrete group and continuous group. So the operation, if the operations are discrete, then it will form a discrete group. If operations are continuous, then it form a continuous group. Example, parity. Okay, parity is a discrete operation. Okay, that's why it will form a discrete group, and multiplication division can be a continuous operation, so it forms a continuous group. So this is group. Now what are Lie groups? Lie groups are nothing but they are a continuous group. They are a form of continuous group which form a differential manifold. Don't go with the jargon word. So what it means is the elements of that group, or the functions that is there, are completely analytical, so that you can differentiate them infinitely many times. And the generators of that group follows a certain relation. That is, they have to be they have to have a commutating relation like that, and they have to have a other commutating relation like that. So these are the basic funda of the Lie group. Now, why I thought about this is that the polymetrics are the generators of that SU2 group. That is what the polarization matrix. So all the polarization matrix for the two-dimensional case can be written in terms of this polymetrics, and that is a type of generator that is of two-dimensional Lie group. So can we ask that if there exists a three-dimensional polarization, there will be a corresponding generator group that is in the Lie group? So means if we can ask that, and if we correspondingly find a relation, consecuting relation of that generator, then we can find the three-dimensional polarization matrix. So let's consider a general three-dimensional matrix. So this is means as you can see, this is 18. It contains total 18 parameters. So if you want to define three-dimensional polarization, so let's consider that we are working with real eigenvalues. So automatically the condition of Hermitian or means decreases the number of arbitrary parameters by 3. So now means we have now we have means more restriction that we want to put is, let's consider it to be a special case that their trace are equal to 0. So so it turns out there are total 8 independent matrices, 8 independent parameters that comes out. So those where we can define this complete three-dimensional matrix, and those 8 independent generators of these matrices are famously called as Gell-Mann matrices. So using now the analogy, so we found that there is something called Gell-Mann matrix, and these are like this. Okay. Now what it turns out that we will use all the previous relation that we use that this polarization matrix like this. So let's define corresponding three-dimensional polarization matrix like this. That's all. This is just by induction. Let's see what happens. So similarly, if we had a polarization matrix in terms of the generators of that SU2, can we define a corresponding? So yes. So we have defined using a Gell-Mann matrices. So this is just a one-to-one analogy that we have drawn, that where we have went from two-dimensional case to the three-dimensional case, and this three-dimensional case can be written, this three-dimensional polarization can be written in terms of like this. Okay, so using the relations now, what are these lambda 0, lambda 3, lambda? So if you remember, the S0 was total intensity. Similarly, this lambda 0 is the total intensity. Okay, and similarly there are.
Anna, excuse me, you have two more minutes.
Okay, sir. So similarly, other also parameter follow. So one that is fixed is the total intensity. After that, since three-dimensional cases will have various contribution like XY polarization state, YZ polarization state, XZ polarization, that can be and correspondingly different components of the linear or circular polarization. So we have all the other lambda tails represents the other polarization parts. So similarly, what we can say is the two-dimensional polarization matrix can be represented by the same formula can be used for a three-dimensional case in order to represent a more vaster, more general light wave, and this can be so this can be this is what I wanted to convey, that means we can generate this three-dimensional state using this. And the bigger question that is why means Pauli matrix came into picture, and is there any is this the point where we can say that there is a classical quantum touch, or is this analogy right, moving from 2D to 3D case? Is there any geometrical understanding related to three-dimensional polarization? As in case of 2D, you can say that there exists a polarization ellipse, you can say. But what we will be able to, can we be able to say that is there any three-dimensional, that is there any ellipsoid or some other hyperspace that have existed, or do there exist? Similarly, can we define an n-dimensional polarization state using this argument? So there are these questions that can be probed in future, and really thank you, really appreciate the time. Thank you.
Thank you, Anand, for this very, very insightful talk. The floor is open for some quick questions. Please feel free to ask. I have a very small question,
Yes,
maybe very elementary for you. Now, these Jones vectors, how they are connected with the Stokes matrix.
Okay, so Jones vector, they are what, if I say, there are like.
So using Jones vector, we can describe linear polarization, circular
Yes,
polarization,
sir.
all this.
It's a more it's a different approach to address the same question.
Okay. So it's there. Is there any linear means direct mapping of these two?
So, sir, finally, means Jones vector also it also is based on the electric field. So
of course.
So same way, if we means if the way we described that the first Stokes parameter that was not dependent on the polarization matrix, but we were able to relate these two using just electric field. Similarly, we can also relate this Jones vector just using the simple.
Okay. I understand. Okay. Thank you.
Thank you, sir.
Any other question? If there is no other question, then let's thank Mr. Anand for this very insightful talk. And let's move on and let's welcome Dr. Hemant Mishra.
Thank you, sir. Thank you.
From Louisiana State University, and for the next lecture. So Dr. Mishra did masters from ISI Delhi and then did his PhD, and currently he is a postdoc at Louisiana State University. And his main research interest includes quantum information theory. So let's welcome Dr. Hemant Mishra.
Thank you so much for the introduction. I'll go ahead, share my screen. All right. Now my slides should be visible.
Yeah, it's visible.
All right. Hello, welcome everyone. First of all, I would like to thank the organizers of QIQT-2022 for this wonderful opportunity to let me present my work. Today's talk is based on my project that is a joint work with Samad Oskoi and Mark Wilty. And as the title of the talk suggests, the talk is about quantifying the performance of continuous variable, unidirectional and bidirectional teleportation through a purely analytical approach. So without further ado, I would like to start with the talk. All right. One of the most fascinating and fundamental protocols of quantum information theory is something known as quantum teleportation, which is the process of transmitting quantum states from Alice to Bob, who are physically distant parties. So the fascinating thing about this protocol is that there is a transmission of quantum information from one place to another place without actually transmitting any physical matter. And this, as the name we have heard, a teleportation in science fiction movies or something, the name teleportation comes from this fact that there's no physical transmission of any matter, just the information. And this sci-fi like protocol is actually theoretically possible, which is given by the 1993 seminal paper by Charles Bennett, in which Charles Bennett et al., in which they laid out the groundwork for quantum teleportation protocol. In their paper, they suggested this teleportation protocol, and they proved that using quantum entanglement, quantum teleportation is actually possible theoretically. So the teleportation that they introduced is as follows. Suppose you have Alice and Bob. Alice wants to transmit an unknown arbitrary quantum state psi to Bob. For that, here's what we should have in hand. Both Alice and Bob should share a quantum entanglement So what Alice does is she takes her share of quantum entangled state and mixes it with the unknown state, and then she does a joint measurement on the two states and gets outcome of the measurement, and then using a classical channel she communicates the outcome of this measurement to Bob. The classical channel can be anything, your internet, your mobile phone, whatever. And then based on the information Bob receives from Alice, he does some operation on his share of entangled state. And then using these operations, he recovers this unknown state that Alice wanted to send to Bob. For those who are, some of you must be familiar with quantum entanglement. For those who aren't, I'll just give you an insight. So quantum entanglement is a quantum phenomena which doesn't have any classical analog. So the idea is that there are ways of entangling two quantum objects, and so that even you take them physically apart from each other, the change in one quantum state influences change in the other quantum state. So this kind of magical thing happening in these two states, which Einstein termed as action at spooky distance. So this is something very fascinating. That is a quantum phenomena. So this whole process, this whole process, transmitting psi from Alice to Bob, this whole assemblement can be treated as quantum channel. Yeah. So since the protocol has been given by Charles Bennett in their seminal paper, there have been several protocols introduced by other physicists, quantum physicists, and there have been a plethora of experiments around the world which have verified quantum teleportation in laboratories. To give you a few examples, there have been experiments starting from 1998, where the experimentalists have been able to transmit optical coherent states, polarization of states of photons, states of qubits, states of qubit using different kind of entanglement. And scientists have been able to teleport electromagnetic field mode using squeezed vacuum states, and so on. Now, depending on, so every quantum system corresponds to a Hilbert space, and depending on the dimension of the Hilbert space, quantum teleportation can be broadly classified into two parts, two categories. If the corresponding Hilbert space of the quantum system is finite dimensional, then the teleportation protocol is known as discrete variable quantum teleportation. And if the Hilbert space is infinite dimensional, then the teleportation is known as quantum teleportation, continuous variable quantum teleportation. And for the sake of this talk, we'll be focusing only on quantum, on the infinite dimension, that is continuous variable quantum teleportation. And there have been work in discrete variable quantum teleportation as well, but there are certain advantages in working with continuous variable quantum teleportation for some experimental reasons that I would not be going into detail. So I'll just recall the teleportation protocol specifically to continuous variable teleportation. Again, you have Alice and Bob, where Alice wants to send an arbitrary quantum state psi to Bob. In this case, both Alice and Bob share a quantum entanglement, which is given by a two-mode squeezed vacuum state. Again, Alice, she mixes her share of two-mode squeezed vacuum state with the arbitrary state using a balanced beam splitter, and then she performs a homodynamic detection on it, and then she gets output, communicates that output to Bob, and based on the information Bob receives from Alice, he performs some displacement operation on his share of two-mode squeezed vacuum state and recovers the quantum state that needed to be sent from Alice. So this is the protocol of quantum teleportation in the continuous variable case. The seminal paper and all the other papers that introduced this teleportation protocol, they proved that there is a perfect teleportation of quantum states without any loss in information under ideal conditions. The ideal conditions in the continuous variable case means that the homodynamic detection should be noiseless. There shouldn't be any interference from the environment, and the two-mode squeezed vacuum state should be infinitely squeezed. So these are ideal conditions. If you can achieve these ideal conditions, the teleportation is perfect. There's no loss of information. But in reality, quantum systems are very fragile to environmental disturbances, and coming up, creating an ideal condition is often quite difficult. For example, there will always be some noise introduced from the environment. And also, we have to work with finite squeezing in the two-mode squeezed vacuum state, because it's physically not possible to have infinite squeezing. So given the limitations of laboratories or in general reality, we can expect that experiments that mimic quantum teleportation will perform less than ideal. So it's a natural as well as important question to be able to say, hey, I have this experimental implementation of teleportation. How can we know that how well it is performing? So every experimentalist would want to know how their experimental setup is doing. This problem had been addressed in the past, and it was solved partially because the earlier work, what they did was they had quantum channels. They determined the performance of that quantum channel by passing through, by letting it teleport some specific class of states, for example, ensembles of coherent states, squeeze states, and all. But remember that the goal of a quantum channel is to be able to transmit an arbitrary state. So in order to truly quantify performance of a quantum channel, we should be able to judge its performance on arbitrary states. We should be able to consider all possible states. So a work in that direction has been recently published by Kunal Sharma, Barry Sanders, and Mark Wilty. In fact, this paper was a motivation for our current work. In their paper, they completely quantified the performance of continuous variable unidirectional teleportation. And the metric that they used, the metric of performance they used, was energy constrained channel fidelity between the ideal quantum channel and its experimental implementation. The method that they used was numerical methods. They used some MATLAB packages to solve the problem and came up with an optimal state that would so given any experimental setup, they proved that there exists an optimal state that if you pass through the channel and see its performance on that particular state, it will give you the overall performance of your experimental implementation, which is kind of fascinating because you don't have to test for all arbitrary states. You just have to find the optimal state and just see how your experimental setup is performing, and you're done. Yeah, so now what we do is as follows. We also quantify the performance of continuous variable unidirectional teleportation, but our approach is purely analytical without using any numerical methods, MATLAB condition. Of course, the results we obtained follows under certain conditions that I will talk about later. And what we do is we also extend the idea that we use in unidirectional case to bidirectional teleportation case, and there also we obtain some partial results. Again, the metric that we used is the energy constraint channel fidelity, which I'll let you know what that is. And the highlight of the results is that in both the cases, both unidirectional as well as bidirectional teleportation, the optimal state that we find is a finite entangled superposition of twin fork states that quantifies the performance of the experimental implementation. Experimentally, these states are quite interesting because one can create these states in laboratories, and yeah, so it is that is why it is experimentally interesting. This can be cooked in laboratories. So I'll quickly walk you through the results and some main ideas that we used in the proofs. For that, I would recall some definitions first. Fidelity is a concept that gives you a measure of closeness between two quantum states. Remember, quantum states are, these are positive semi-definite operators with trace 1. And fidelity of two quantum states, rho and sigma, is defined as the product of their square roots, the square of the trace norm of the product of their square roots. So, and if you see, if rho is equal to sigma, then you have square root of rho times square root of rho, which gives rho, and its trace is 1. So you take square, it's 1. So fidelity between rho and rho is 1. And if you take two states which are orthogonal to each other, like their product is 0, then the fidelity turns out to be 0. So you have, so this fidelity takes values between 0 and 1. The closer this value to 1 means the closer the two quantum states are. The closer this value to 0, that means the more distinct the quantum states are. So in this sense, this gives you a kind of measure of closeness between two quantum states. Now, using fidelity, one can define a measure of closeness between two quantum channels. Mathematically, quantum channels are completely positive trace preserving maps, so that a quantum channel acting on a quantum state gives you a quantum state. So that is the mathematical definition. And so there is something called energy constraint channel fidelity between two quantum channels M and N, which is defined as the infimum of the fidelity between the outputs of these two channels. And the infimum is taken over all the states satisfying this condition. Here, HA is the Hamiltonian of the system, and the trace HA times phi A, where phi A is defined as the partial trace of phi RA. This inequality means that the energy in all these states in mode A is less than or equal to E. So that is why the energy constraint thing we have. And if we observe it closely, what we are doing is we are taking the fidelity of all possible states, that like their outcomes through these channels, and take the infimum. So this quantity is a lower bound on the fidelity between the outputs of any two states through this channel. So this kind of gives you the worst case scenario for the two channels. Like you take any state and take their outputs through these two channels, find their fidelity, that fidelity will be lower that will be bounded from below by this quantity. And so, and that means that the two channels in the worst case will give you this number. So kind of gives you a measure of distinctness or closeness of two quantum channels. So this is the idea of energy constraint channel fidelity. Let's go to unidirectional teleportation. Again, under ideal, unidirectional teleportation means transmitting quantum state from Alice to Bob. Under ideal condition, we know that there's a perfect transmission of quantum states. So that is represented by the identity channel, which can be seen from this diagram. And an experimental implementation, what it does is this also transmits quantum state from one Alice to Bob, but there are some noisiness or finite squeezing in between. So that is represented by this channel. We call it additive noise channel. Here it is represented by script T from A to B. And this parameter xi is a non-negative number which encodes the finite squeezing and the noisiness in the detection. So it kind of gives you like, and if xi is 0, then this is your ideal, this is the identity channel. And as xi increases, that means there is more noise in your channel. So this kind of, this is a parameter that gives you the noisiness and the finite squeezing. Now, what we are interested in is that we want to compute how close this experimental implementation is to the identity channel. And for that, the metric that we use is the energy constraint channel fidelity. Using the definition, we compute the energy constraint channel fidelity between the identity channel and the additive noise channel is equal to the infimum of the fidelity between the outputs of these two channels. And the infimum is taken over all states psi, satisfying this condition. This is the energy bound condition, which in this case says that the average photon number of states in mode A is less than or equal to E. So with this definition, we are interested in computing this quantity, what this quantity will be, and for which quantum state is this quantity attained. So a work in that direction shows that the infimum in the energy constraint channel fidelity can be restricted over a special class of states. So remember, we have this energy constraint channel fidelity. It can be shown that even if you restrict the infimum to pure states, which are given by the following, it is, so this is like infinite sum, which is also known as infinite entangled superposition of twin Fock states. And here this equality means that these are states, the sum of the squares of lambda should be equal to 1, and they're all non-negative numbers. And this inequality here means that the average photon number is less than or equal to E. So this is really nice because now we are dealing with some specific kind of states. And so this is nice. I'll tell you why. So now note that this is an infinite dimensional problem because these sums run from 0 to infinity and everything. So what we do is we chop down this problem and truncate it to a finite dimensional problem. So what we do is, instead of the infinite dimensional version, we consider a finite dimensional version of this problem, which is defined as exactly the previous one, this one, where the infimum is taken over pure state psi Ra, satisfying these conditions. These conditions are exactly the same as the previous one, where the infinity is replaced by a positive integer m. And we call it the truncated energy constraint channel fidelity between the ideal channel and the experimental implementation. What we do is, now that we are dealing with finite dimensional problem, it makes our life simpler. In fact, we, in our work, compute the expression for the fidelity between these two channels, these two states for such states, and solve it mathematically, purely analytical approach, and we get the following result for the finite dimensional truncated version of the problem. We show that, so mathematically we have this problem. We show that a solution to this truncated problem is given by this state under this condition on the energy, this condition on the energy bound E. If E satisfies this condition, you take this state psi. This will give you the truncated energy constraint channel fidelity, meaning this infimum is attained at this simple looking state. Now, an interesting and a very good news about this result is that the state is independent of the parameter m. Even though we have truncated the problem to m parameter, the solution that we obtain is independent of m. That is a really good thing for us, because there are inequalities known that relate the finite dimensional truncated version of the problem to the infinite dimensional problem given by these inequalities. Now, these inequalities can be found in the paper I showed by Kunal Sharma, Barry Sanders, and Mark Wilde. We have these inequalities already. So, and we also know that these highlighted parts, these quantities are independent of m. So what we do is we simply substitute the values of these quantities in these inequalities and take the limit m tending to infinity, and then using sandwich theorem, like the left hand and right hand quantities come out to be same, so the middle one has to be equal to both of them. So just using these two simple ideas, we obtain the result for the original problem. It states that the optimal state that quantifies performance of unidirectional teleportation is given by this twin fork finite entangled superposition of twin fork states whenever the energy satisfies this condition. And this is the energy constraint channel fidelity between the ideal channel and the experimental implementation. So this was the result for unidirectional. We extend our ideas to bidirectional teleportation as well and have some results. Here's what we do. Now, ideally, by the way, a bidirectional teleportation is a combination of two unidirectional teleportation in which Alice transmits quantum information to Bob, and Bob also transmits back quantum information to Alice. So, and this can be represented by a tensor product of identity channel from A to B with the identity channel from B to A. So this is kind of swapping of states. So this is also known as the swap channel. And again, an experimental implementation of bidirectional teleportation can be given by a combination of two one-directional teleportation, which again is given by a tensor product of two additive noise channels with parameters xi and xi prime. Now, again, what we do is we compute the energy constraint channel fidelity between the swap channel and the tensor product of the additive noise channels, which by definition is given by this quantity. Now, the infimum in this case, just like in the case of unidirectional teleportation, can be restricted to much simpler states. It can be shown that we can restrict the infimum to these simple looking states. Again, we have these 4 conditions where these summations run from Mn from 0 to infinity, Mn from 0 to infinity, and everything, just like in the unidirectional case. Again, what we do is, this is an infinite dimensional problem. We focus on its truncated version of the problem, which is defined as this: the truncated energy constraint channel fidelity between the swap channel and the tensor product of the additive noise channels. It can be shown that I'm sorry. So this is the truncated version of the problem, where we consider infimum or all pure states given in this form, where all the infinities are replaced by M. Again, we focus on solving this truncated version of the problem, and hopefully we should be able to give the solution to the infinite dimensional problem. So it turns out that the more general case, so we have here xi and xi prime. In our work, we find a solution when xi is equal to xi prime, which means that the quantum channels in both the directions that is being used is the same channel, which is experimentally relevant scenario. And the more general case where xi may not be equal to xi prime is an ongoing work. And we hope to obtain some results there, maybe. So now that we have a finite dimensional truncated version of this problem, again, using similar ideas, the mathematics is quite different, but the ideas are the same. We solve the finite dimensional problem, and we show that the optimal state in the bidirectional teleportation case turns out to be, again, this simple looking state when the energy bound satisfies this condition. And in this case, the channel fidelity that we obtain is given by this quantity. Again, an interesting thing to notice is that this quantity, this energy constraint channel fidelity, is independent of the parameter M. So just like in the unidirectional case, if there were any inequalities that relate the finite dimensional problem with the original problem, our life would be easier. We didn't find any inequalities, so we went ahead and derived our own inequalities, which is like similar looking inequalities as in the unidirectional case. We showed that the original channel fidelity can be bounded from above and from below by these 2 quantities. And again, whenever xi is equal to xi prime, by the way, our inequalities are for general xi and xi prime. So in future, we have these inequalities available to us. But for the time being, when xi is equal to xi prime, what we do is we substitute these values of the finite truncated version of the problem and take limit m tending to infinity. Again, using sandwich theory, we get the value of the energy constraint channel fidelity in this case. So here's the result. Our result says that given any experimental implementation of bidirectional teleportation, there exists an optimal state, which is a finite entangled superposition of twin Fock states again. And under these conditions, these states quantify the performance. And the energy constraint channel fidelity expression is given by this expression. So this is our result for the bidirectional case under the special condition. I would like to bring your attention to the results that we have for unidirectional as well as bidirectional case and try to see some similarities. Like in the unidirectional case, the condition on the energy bound that we have is this. And in the bidirectional case, we have the exact same bound on 2E instead of E. So these 2 quantities are same. Now, going back to the optimal state that we obtain in the unidirectional case, looks like this. Superposition of these 2 states, 0, 0, 1, 1. And in the bidirectional case, the optimal state that we obtain is like similar looking state. And the energy constraint channel fidelity expression that we obtain, we can see that how closely they resemble with each other with some modifications. So even though our results are experimentally interesting, they're mathematically beautiful. So just something that makes me happy. Yeah, and this would end my talk. And for future work, one could work on the more general case, which we actually are working, and hopefully we'll get some results. All our results were given for some conditions on E. It would be interesting to come up with an optimal state in the bidirectional teleportation with some relaxed conditions on the energy bound E. Would be an interesting work. Perhaps one would have to use some numerical method MATLAB package like one used in the paper by Mark Wilde in their unidirectional case. Perhaps we can solve this problem for bidirectional case as well in whole its generality. And one could also extend this thing to n-directional teleportation, where instead of 2 parties, you have n parties, and there is teleportation between any 2 randomly chosen parties. This finishes my talk. If you have any questions, I would be happy to take, and thank you for your attention.
Mishra, for this exciting talk. I must say the results looks really very beautiful, very elegant.
Thank you.
So the floor is now open for question. Any question, please feel free to ask. So I have just a small curiosity. Say, as you were saying that your zeta equal to zeta, not equal to zeta prime is your future outlook you are working on.
Yes.
So, do you have any hunch of what kind of changes you may see?
Oh yeah. So this is still an ongoing, and we are still in the initial phase. We have found a result in the case xi may not be equal to xi prime. The result even though we have the result, we still need to refine it, like see some connection there. But we have got something, but it's not fully baked yet. Yeah.
Thank you.
And yeah, it's an interesting question. In fact, even in that general case, the optimal state that we find is a finite entanglement of twin Fock states under certain different conditions on the energy bond. Yeah.
That aim, independence of aim, that still remains valid.
Oh yes, it does.
Okay. Okay.
Yeah, because remember the inequalities that we showed. Oh yeah. So what you're asking, I got that. Yeah, that remains. Yes, that is why the proof works.
Okay.
Yeah.
Thank you.
I think this is what you were asking. If this holds true when xi is not equal to xi prime.
Yeah.
Get this.
So that capital M. So you have showed that the results are then independent of capital M. So that still holds.
I'll have to check on that. I mean,
okay.
As I said,
yeah, I understand. This is an ongoing work. This was just my curiosity.
Yeah, it was a nice.
Yeah. Okay. Any other question? Please feel free to ask.
Yeah, I mean, ideally it should be. I mean, that is what we are hoping.
Yeah, I had the same feeling.
So I have a question.
Yeah, please.
Yeah, you said that CV teleportation is more easy, and DV teleportation is there are many challenges in DV teleportation. So can you tell me that why is that?
All right, first of all, full disclosure, I'm not a physicist, I'm a mathematician, so I might not be able to satisfy you with my answer. But from what I know, it seems that I don't know about the challenges, but I have some ideas about the advantages. That it's easier to, I think, produce more entangled states in continuous variable case, and it's just easier to work with in laboratories, I guess. What are actual advantages or disadvantages per se? I don't know much.
Okay,
Sorry
thank
about
you.
that.
Yeah, thank you.
Okay, thank you. If there is no more question, then let's thank Dr. Mishra for this enlightening talk. And also, I'd like to take this opportunity to thank all the speakers for the evening session. And with this, let's close this session for today. Thank you very much.
Thank you.